Hi, my name is Katie Wong, and I'll be covering my oscillations lab. The purpose of this lab is to analyze the position of a spring mass system oscillating in two dimensions and calculate the energy changes of the system. At the end of the lab, I could determine that the energy principle is satisfied, meaning that the total change in energy of the system equals zero. One principle we use is Newton's second law, which includes the momentum principle, which can be used to derive the velocity and position update formulas. We use Newton's second law here because we need to find the net force acting on an object by summing its forces from interactions with other objects. Another principle we use is the energy principle, which allows us to calculate the change in kinetic energy, gravitational potential energy, spring potential energy, and total energy. On the slide, I have listed out the general formulas for the changes in these energies, but we still need to think about the initial and final conditions of a state to determine the changes in energy. I used the video provided to us, so I made my system the mass, spring, and earth, meaning nothing is in the surroundings. So this allows us to set the total change in energy to zero. For the initial conditions, I have them all listed out on the slide. You can see how I set up the coordinate system in Tracker and the graph of the data collected in Tracker. For the computational model, I plugged in the initial conditions I mentioned in the previous slide and used the formulas to find the kinetic, potential, and total energy. I also used Newton's second law to find F net equals the sum of the force of gravity and the spring. Then, using the velocity update formula, I calculate the object's new velocity and use that to calculate the ball's new position in the position update formula. Next, we updated the spring's position and stretch. And then finally, we updated the new energies of the system. Here's the data from the computational model and the observed data on one graph. Notice how for the position graphs, the experiment roughly models the computational model. However, if we look closely, we will notice that as the experiment goes on for a longer amount of time, it deviates more from the computational model. This suggests that in the real world, our experiment was not a true closed system as there were other forces present acting on the mass, such as drag, which was not accounted for. Another possible error source is human error when locating the center of mass of the object in Tracker. For our what does it mean question, we can see that the energy principle is satisfied because the change in energy is approximately zero throughout the entire time. Note that this means that the kinetic energy will cancel out with the gravitational and spring potential energies in the sum of the total energy. For the next part of our what does it mean question, I found the oscillation periods using the x and y graphs by looking at the time intervals between the peaks of the data. Notice that the period of oscillation is slightly different depending on whether you use the x direction versus the y direction. So this means that we will have lots of deviations since the period of oscillation is used to calculate the spring constant, which affects the spring force, net force, and kinetic energy. So in conclusion, we used Newton's second law and the energy principle to determine if the energy principle was satisfied in our experiment. We analyzed the position of a spring mass system oscillating in two dimensions. We calculated the energy changes of the system. And we noticed that in the real world, real systems may not be closed even if theoretically they are.